Imagine standing at the base of a skyscraper during an earthquake. The ground rumbles, the building sways, yet it doesn't collapse. How is this possible? Welcome to Civil Engineering Edge, where we unravel the hidden science behind the world's strongest structures. Today, we're diving deep into one of nature's fiercest battles: concrete versus earthquakes. From brittle failures of the past to futuristic innovations, we'll uncover how engineers have transformed fragile stone into unshakable giants. Let's begin our seismic journey. Unshakable foundations, the earthquake paradox, visual. Archival earthquake destruction gives smooth cut to modern skyline. Throughout history, earthquakes have left behind tragic images of collapsed concrete buildings, symbols of fragility. Yet today, concrete is not only trusted, but celebrated as a primary material in earthquake-resistant design. Here lies the paradox. How does something seemingly brittle become the very backbone of resilience? Concrete on its own is hard, heavy, and rigid qualities that make it excellent under compression, but notoriously weak under tension. So why are today's concrete towers still standing tall after violent tremors? The answer lies in engineering breakthroughs that redefined how we think about structure and strength. Early failures taught us harsh lessons. Rigid, unreinforced concrete crumble like chalk when shaken. But modern skyscrapers are not the same story. Hidden within their elegant facades is a carefully orchestrated system where strength meets flexibility and design meets science. This transformation didn't happen overnight. Over decades, engineers studied seismic forces, mapped how buildings vibrate, and innovated to make concrete act less like brittle stone and more like a living, adaptable shield. So, what changed? The secret lies inside the concrete itself: the reinforcements, the hidden cages of steel, and the science of ductility. Let's unravel how concrete got its steel spine. Rethinking reinforcement. From sticks to steel spines, concrete alone is strong, but earthquakes demand more. When the ground shakes, structures are pulled, twisted, and stretched. That's where reinforcement steps in, the unsung hero hidden beneath the surface. Enter rebar, steel bars embedded in concrete. Unlike brittle concrete, steel excels in tension. Together, they form a composite material capable of resisting both pushing and pulling forces. Think of rebar as the building's muscle fibers, strategically placed to resist the forces of seismic tug-of-war. But rebar is only the beginning. Earthquakes don't just pull, they twist and buckle. This is where stirrups and ties play a vital role. These small steel rings, wrapping around rebar columns, confine the core concrete like a protective cage. They prevent cracks from spreading, keep the steel from buckling, and give columns the resilience to endure violent shaking. Picture it this way: without reinforcement, a concrete beam is like a brittle twig. With rebar, stirrups, and ties, it becomes a reinforced spine, strong yet flexible. This hidden skeleton of steel is why today's buildings just crumble at the first tremor. But strength alone isn't enough. Resilience lies in flexibility. To understand that, we must go beyond reinforcement and into the philosophy of flexible design. Beyond the basics, flexible design for a shaking world. In seismic engineering, rigidity can be dangerous. If a building is too stiff, it resists movement until it suddenly snaps. The true secret to earthquake survival lies in ductility, the ability to bend and sway without breaking. Engineers design concrete structures not to resist every ounce of seismic energy, but to dissipate it. Instead of absorbing shock like a brittle object, these structures sway gracefully, channeling forces harmlessly through their framework. Central to this design are shear walls, thick vertical slabs integrated into buildings. Acting like a spine, shear walls help distribute horizontal earthquake forces evenly. Similarly, diaphragms, often the floors or roofs of a structure, act as horizontal shock absorbers, transferring loads safely across the framework. This interconnected system allows buildings to behave like living organisms during an earthquake. Floors, beams, columns, and walls all work together, flexing and stretching while maintaining stability. So, while a swaying skyscraper might look terrifying, that very movement is its greatest defense. By flexing instead of resisting, the structure preserves its integrity and protects the lives inside, but engineers didn't stop there. Beyond traditional design lies a realm of groundbreaking innovations technologies that make buildings not just resilient, but revolutionary. Shake, rattle, and roll. Advanced seismic innovations, modern seismic engineering has moved far beyond concrete and rebar. Today, buildings are equipped with futuristic systems that actively combat earthquakes. One such marvel is base isolation. Instead of anchoring a building rigidly to the ground, engineers place it on flexible bearings. When the earth shakes, the base moves, but the structure above remains relatively still, almost as if the building is floating. This technology has protected hospitals, skyscrapers, and even cultural monuments. Another breakthrough is damping systems. Think of them as shock absorbers for skyscrapers. Tuned mass dampers, massive weights suspended inside towers, sway in opposition to the earthquake's motion, reducing vibrations. Viscous dampers filled with fluids absorb energy and convert violent motion into harmless heat. These innovations are engineering's way of fighting nature, with nature turning motion against motion to safeguard lives. But the story doesn't end here. The future promises even greater resilience. The future is resilient, building for tomorrow's quakes. As earthquakes grow in intensity, so too does human ingenuity. The future of seismic engineering is filled with smart, adaptive solutions. One frontier is smart materials like self-healing concrete, capable of sealing cracks automatically, prolonging structural life. Sensors embedded in buildings now allow real-time monitoring of stress and vibrations, enabling immediate responses during and after seismic events. The evolution of earthquake-resistant design is not static. Every disaster teaches engineers something new. Lessons from past collapses reshape building codes, inspire innovations, and guide us towards safer structures. The future may see buildings that adapt dynamically during earthquake, structures that stiffen when needed, or even redirect forces through active control systems. What began as a struggle between brittle stone and unstoppable nature has now become a sophisticated dance of science, technology, and resilience. Concrete structures no longer stand in defiance of earthquakes, they move with them, ensuring safety and survival. Our concrete giants are not unshakable because they resist the quake. They endure because they embrace it. From hidden steel spines to futuristic base isolation, we've uncovered the incredible journey of how concrete structures withstand earthquakes. What once crumbled under nature's fury now sways, flexes, and survives. The science of resilience continues to evolve, making tomorrow's buildings safer than ever. If you found this fascinating, don't forget to like, share, and subscribe to Civil Engineering Edge for more insights into the marvels of modern construction. Until next time, stay curious and stay resilient.